Aristotle thought that when things were falling onto Earth, this is Earth and this is an object falling. If I am exerting a force in this particular direction, then the equal amount of force is being exerted in the opposite direction. That is why there is a negative sign. Momentum indicated by the letter P is actually a vector quantity, which means it has a particular value, it has a particular direction, and it obeys laws of vector addition. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And today we are going to dive into a whole new chapter, that is laws of motion, pioneered by none other than the famous scientist Newton or Isaac Newton. So we are going to dive in and understand the world in the eyes of Isaac Newton, or the way Isaac Newton saw the world. So we are going to basically learn Newtonian Mechanics 101. So before getting into Newton's perspectives, we have to first understand that how physics actually evolved. I'm not going to take a long time, but I'm going to give you a short description on how physics got to Newton before passing on through some other hands. So initially, let's say 200 years before Isaac Newton, there was a scientist or a philosopher mainly named as Aristotle. So Aristotle believed that there are certain theories that govern certain properties in the world. So there was not really other people who was looking into physics and understanding physics at that. So Aristotle actually came up with a few theories regarding physics. For example, he thought that, like we all know how gravity and the forces of attraction are the main theories that put forth by Newton. Just like that, Aristotle also thought about these things 200 years before Newton. But the only problem was that it was, let's say, a bit diluted. That is, Aristotle thought that the things that fall onto Earth, that is, Aristotle thought that when things were falling onto Earth, this is Earth and this is an object falling. So when things were falling onto Earth, Aristotle believed that the only reason why things fell onto the Earth was because the objects that fell onto the Earth had a strong yearning for Earth. That is, from a philosopher's standpoint of view, maybe, but from a physics standpoint of view, now we know that that is not really the reason why things or objects fall onto the Earth. Now, the second observation made by Aristotle was that things in motion tend to stop. That is, if you roll a ball or if a person runs or any object is moving in a plane, it tends to stop because the object gets tired. That was Aristotle's next incredible finding. That is, if there was a plane and any object was moving in that particular plane, it slowly came to a stop because the object was tired. This brings to your attention that how physics was actually perceived in the 1400s or 1500s. That is, by the time of Newton, physics took a drastic turn. Until then, physics was not understood perfectly. So initial conditions for Aristotle was that he thought that objects fell onto the Earth because the object had a strong yearning for the Earth, and object in motion tend to stop because the objects were getting tired. Obviously, we know that this is not the right thing, but Aristotle thought that this was the right thing. And it wasn't like for almost 200 years, theories like this actually stood as physics theories or actual theories that people actually believed. It was not until by the arrival of Galileo Galilei and certain other people that people started to rethink these things. So Galileo Galilei and other people actually conducted experiments regarding this particular observations, and they actually found out that, okay, these understandings or these prevalent theories were actually wrong. So Aristotle's experiments or Aristotle's philosophies were actually inaccurate and basically wrong. So basically we can say that Aristotle came up with a whole new things which was completely wrong. Galileo fixed it a little bit. Newton came and completely fixed it. So what Galileo believed was that, okay, so Galileo understood that there was something you have to study in terms of motion and the objects falling onto Earth. So he saw that when you rolled an object like this, okay, it keeps on rolling and it stops after some time. And similarly, when you increase the plane, that is, if you tilt the angle, that is, if you make an angle like this, if you make the sliding path, the trajectory like this, a curved path, then it was observed that if no force, no external force was given onto this particular ball, then the ball would roll to the same height and it will come back. It did not go even further than the initial height it was dropped from, given that there was no external force applied. And he also calculated certain calculations based on objects in free fall, that is, object falling under the influence of gravity. He postulated that two objects may simultaneously reach the ground. There is no difference in between. All these was small experimental conclusions of Galileo Galilei. It was not until a few more years later that Newton came onto this show. So Newton came onto this show, might I add, he actually invented his own mathematics to prove his own theories. So he was very young, he was very smart, and he also came up with the math which you all hate. That is calculus, differentiation and integration. He was actually 23 years old when he invented differential calculus and integration and all other things. Anyways, so Newton actually came up with all of these new laws in order to understand motion and how objects behave the way they do. So actually we can say that Newton actually saw the world in terms of lines of actions, lines of forces. He actually saw the world in terms of forces which were acting upon one on the other. He explained the behavior of certain particles, certain motions, certain trajectories based on this particular force. So based on these conclusions, he actually formulated three laws, which was later known as Newtonian laws or simply Newton's laws of motion. And that is what we are going to study in this particular chapter, that is laws of motion, that is found by Isaac Newton. So the first thing you have to understand is that first Aristotle came up with some absurd theories which was completely wrong, and then Galileo Galilei came and he proved some things which had some sense in it, like the objects in motion and the object, while objects are moving, they are influenced by a force and they are under the control of these forces. Depending on these forces acting on these objects, the motion of these objects are controlled. All these came into effect, that is, the ball began to roll under the observations of Galileo Galilei. And then came Newton, who revolutionized the entire world with his single paper, that is Principia Mathematica. But for now, we'll only study about his main laws. So let's get right on to it. So everybody knows Newton's first law of motion, that is, every body continues to be in a state of rest or uniform motion unless or until it is compelled by an external force. What does that actually mean? It means that Newton observed something. Okay, Newton was looking at an object and he said that, okay, there is a chair. There is a chair like this. There is a chair like this, and that particular chair is not going to move until I push it. That particular chair is not going to move until I push it, or something comes and moves that chair. Until then, that particular chair is not going to move. That is Newton's first law of motion. We all know that, right? We know that if no force is applied on this particular object, no one is going to move that particular object is going to be there stationary at rest at all times. That was the first observation Newton made. So we can say that if no force is applied on this particular object, that particular object is not going to move. What is so great about that, right? The great thing about that was that the thing that followed. What about things in motion? So Aristotle believed that things in motion tend to stop because they get tired. But now we know that that is not actually the case. Newton actually observed this and came up with a clever definition for this. So objects in motion actually tend to stop also if there is a force being applied. If there is no force being applied, that particular object in motion will continue to go in that particular motion. That is, if an object is executing a uniform motion, that is, an object is going with constant speed or constant velocity, then that particular object will keep on going with that particular constant speed or constant velocity in that particular direction until an external force is there to oppose that particular motion. That is actually true in the case of every daily object. That is because we know now that if there is a plane like this and a ball is rolling like this. That particular ball comes to a stop only because there is tiny imperfections on the floor that is known as friction. So this particular object comes to stop because frictional force is acting on that particular object, asking it to stop. We know that. You can imagine it as a bumpy road much more clearly. So in every surface, there is actually small imperfections inside that particular floor or smooth surface or any surface. That particular frictional force is opposing that particular motion of any object. In this case, the ball's relative motion is actually opposed by the floor, and that is why the ball stops. Maybe it is also because of the wind resistance. When wind is blowing, the object tends to slow down. In all these particular cases, you have to know that external force is applied in the form of frictional force, in the form of wind resistance. That is why you can take a paper and just swing it around, or you can keep your hands outside when you're going in a car or any other vehicle. Please don't do that, but you can, and you can feel the wind blowing against you. You can feel the force that is exerted onto you. Just like that, wind or frictional forces actually exert a force onto this particular object, which makes this object not to move. That is, oppose that relative motion. So you have to understand that if there was no force present, that is, if there was no wind resistance present, if there was no frictional force present, then this particular object which was in motion would have kept on going in a particular line. That is, it would keep on going in that particular line forever and forever and forever until any other object or any other body or any other system exerts a force on it to change its direction, to change its momentum. What is direction and momentum? Everything will be explained. But yeah, for any object to have any particular change in its motion, a force has to be applied. That is Newton's first law of motion. Seemed pretty simple with the chair, right? But inside that, all of these quantities are hiding. So we can say that every object remains in a state of rest or uniform motion until or unless it is acted upon by an external force. It is very important that it is an external force and not any other force, because internally we cannot apply any force to change its direction. This ball cannot just change its direction just like that. It has to be an external force acted upon to change its particular direction. So that is Newton's first law of motion, and a clear example that everyone knows is that how we tend to move forward when a vehicle is suddenly braked. For example, if you're going in a bus, initially, let's say I'm in a bus, I sat and I slept, and when the bus suddenly took off from rest, then my head will go backwards, right? Because even though the bus is starting to go forward, my body has the effect of Newton's first law. So my body continues to remain in a state of rest, but the external force is trying to push me forward. That is why I go backwards. And when the object is moving, when the bus is moving and suddenly it brakes, what happens? My body was in continuous motion, and when the external force of braking was suddenly applied, my body had a tendency to continue in that state of motion. That is why my body suddenly went forward when it is suddenly braking. Retake. When it suddenly brake, retake. When the brakes were applied suddenly, that is why my body fell forward, or I had to move forward only because of that particular consequence. So we can actually say that there are two states hidden within this particular law. That is the state of continuing in rest or the state of continuing in motion. So we can actually say that there are two possibilities or two subvariants to this particular law. And this particular law then can be called as, law of inertia. Law of inertia just means that it is the law where an object continues to be in a state of rest or uniform motion unless or until acted upon by an external force. So it can continue to be in a state of rest or uniform motion. So depending on that, we can say that we can classify this into two sectors. That is, one is inertia of inertia of rest and inertia of motion. Your book gives these two definitions. Your NCERT dictates that there is inertia of motion and inertia of rest, but law of inertia itself is sufficient. You just have to know that an object which is in motion will continue itself in that particular motion, or an object in rest will continue itself to be in that state of rest unless an external force is acted upon it. That is law of inertia. And the examples are very simple. If you know your mother takes out the carpets and she'll hang it over something and she'll start beating it up. So you can see dust falling from that. Or you simply doing this with your towel which is wet, then you can actually see water droplets, or in the case of carpet, you can see dust falling from that particular carpet. That is because when you suddenly move that carpet, when you suddenly dust that carpet, what happens is that when you suddenly hit that carpet with anything, the carpet is actually moving. But the objects, that is the dust particles which is attached to that particular carpet, has inertia in it. So because of inertia of rest, that particular dust particles will remain in its initial position, and while you're beating the carpet, what happens? This is the dust particle, this is the carpet. While you're beating the carpet actually moves backwards, but the dust particles which has inertia of rest falls down under the influence of gravity. So that is one famous example for inertia of motion and inertia of rest. And the same thing can be said about wet towel that is being shaken abruptly. So many examples are there. That is all about law of motion, that is first law of motion, or simply known as law of inertia. Again, before getting into Newton's second law of motion, I'm going to directly take you into Newton's third law of motion, simply because it's much more easier and relatable for you guys. So what is Newton's third law of motion? Everybody knows this. Everyone in this entire world who knows little bit of physics actually knows this. That is, every action has an equal and opposite reaction. So, or mathematically we can say that it is F12 is equal to minus F21. So what is this 1, 2 and minus F21? For that, we need to understand how Newton saw the motions having a repeated resulting backwards effect. That is, the famous example everyone knows is a perfect condition where there is no friction. For example, imagine that there is a lake like this, and here is the surface, and there is a boat which is on the lake. It is comparatively a light boat, only fit for one person to travel in it, and it is made up of fiber. So let's say a person is standing here on the boat. Okay, this person is standing here on the boat and he doesn't want to get his shoes wet. So what will he do? He'll just jump onto the ground. So how will he jump? He will jump by applying a force, a downward force onto the boat, so that a force is experienced onto the boat and he will jump forward. So you know, right? If you want to jump, you will exert a force downwards and then you will exert that force in maximum effect so that you can jump. So what actually happens if you observe this entire scenario is that while he's applying a force onto the boat and he's jumping across, what happens is that the boat actually moves backwards. The boat actually moves backwards, not by a kilometer or something, maybe 1 or 2 inches, maybe just 1 centimeter. But the point is that the boat actually moves backwards and the person actually jumps forward. I don't understand it. What does this have to do with Newton's third law? Newton's third law actually states that for every action, here the action is jumping forward. So every action, there is an equal and opposite reaction. So here the opposite reaction is the boat going backwards. So the action was going forward, but the boat went backwards. So that combined effect, a pair of equal and opposite forces acting on the same body, that is known as Newton's third law. This is visible everywhere. If you want to jump up, that is, if you're standing on the floor and if you want to jump up, what happens? You're exerting a force down onto the floor And when you are exerting a force down onto the floor, the resulting force is also there in the opposite direction. That is why you can stand up, because you know that the earth is pulling you down with its gravity, right? We'll get to that also very soon, but you know that earth is pulling down with you with a particular force. It is pulling you down with acceleration due to gravity, but you're not falling. Why? You're not falling onto the earth. Here I'm standing in a recording studio. I am teaching you guys. I think you're learning, but again, I'm trying to tell you a concept, but I'm not falling onto the floor that is below me. I'm not falling onto the gutter. I'm not falling onto the road. Why? Is it because I'm really strong? Is it because I can float? No, right? There is a floor below me. That is why I'm being able to stand up. But why can I not break the floor? Why do not I make a hole in the floor and fall down? It can only happen because of one single thing. That is, the floor is actually exerting an equal amount of force in the opposite direction so that it balances out my force. That is, you know that I have a particular weight and I am exerting that entire weight times acceleration due to gravity on the floor. So I'm exerting a force onto the floor. And because of that particular force, I should go down. But I'm not going down. You know that if this pen is here holding in my hand like this and I'm applying a force, the pen is going down. Right? It is going down. Just like that, why am I not going down? Because you can say that, okay, there is a floor, that is why you're not going down. But again, if I do the same thing here, the pen is not going down. Same logic. Why? Because my hand is stopping it. But stopping it how? It can only be stopped when I apply a force, let's say a 5 newtons onto my hand like this. My other hand should also exert the same force in the opposite direction. If not, if I'm applying too much force, then this hand will go down. But in this particular case, even though I'm applying a force, my hand is not going down. That is because my hand is actually exerting the same amount of force in the opposite direction. So you can say that even though I'm applying a force downward, I'm not falling or I'm not sinking to the ground because an equal amount of force is being exerted in the opposite direction. Is it like someone is purposefully exerting that force? No, it is a basic fundamental reality. That is, if you apply a force on anything, any object, that particular force is being reapplied onto you. That is just a basic fact. And that was the observation that Newton made. And he concluded that, okay, if one body is applying a force onto another body, then the equal amount of force is received from that particular body in the opposite direction. That is, if I am pulling on something or if I am pushing on something in one particular direction, let's say there is one body here and one system here and I'm pushing on it, then the system actually exerts the same amount of force in the opposite direction. That is what just Newton said. That is the simple definition, that is, every action has equal and opposite reaction. If we take the example of the boat and the person jumping on from the boat to the ground, we can say that intent or the result of this particular experiment or this particular motion was that it is in the forward direction, like the person is jumping onto the land. So here it is in this particular direction, but the boat is actually moving in the opposite direction. It is moving in the opposite direction. The person is jumping forward, the boat is moving backwards. So it is a pair of equal and opposite charges. It is not like the boat will have more force than the force you have just exerted. Or you won't have extra force which you suddenly accumulate during the jump. No, it's not like that. Whatever force you are exerting, you will get in back or you'll get in return the same amount of force that you just exerted. That is the basic assumption behind Newton's third law of motion. The only thing is that Newton defined it in terms of two bodies. So we can say that if 1 is indicating body number 1 and 2 is indicating body number 2, then we can simply say that Newton said that if you apply a force, if the first body applies a force onto the second body, then we can say that the second body, that is the second body, will also apply a force onto the first body with equal amount of force just that it is in the opposite direction. So depending on this, you can clearly define Newton's third law of motion. If you want a clearer example, assume that you are in perfect vacuum, that is, you are in space. You are in space and there are two people in space playing catch. So there are two people in space playing catch. Let's say this is me and this is my best friend JP, Vishnu J. Prakash. Anyways, so what happens is that I have a ball in my hand, I throw that to him. So while throwing this ball onto him, what happens is that, imagine that I'm in space, which means there is no friction, there is no gravity. There is gravity, but I'm experiencing forces of gravity equally in all directions. Let's just assume that there is no gravity felt on me. But anyways, so I'm throwing this ball towards him. So what is happening? I'm exerting a force onto this ball. I'm throwing this ball with a force of F. But if you do that, what you can actually observe is that while the ball is actually moving forward towards him, let's say the ball is actually moving towards him, what simultaneously at the very same instant what happens is that I will also move backwards. So if I throw a ball towards him in space, what will happen is that I will go backwards. This will actually prove, you can actually do this if you ever go to space. Or you can create a situation where you apply a force onto something, you will experience that same force backwards. So what happens is that when I throw the ball forward towards my best friend, what happens is that the ball is simultaneously exerting a force onto me. That is, when I am exerting a force onto the ball and I'm throwing on it, the ball is also exerting a force onto me in the opposite direction. And I will move backwards. That is because it is a consequence of Newton's third law of motion. Just like in the case of a boat and the person who's jumping on from the boat, here if there is no friction, no air resistance, completely vacuum, then I'll also experience this force much more clearly. You can also try it on walls. If you push on the walls, you can feel the force coming back onto you. That is because of, again, Newton's third law of motion. If you give any force to any body, same amount of force will be returned onto you in the opposite direction. That is Newton's third law. And what is this particular direction thing? Okay, I'm pushing onto a body, so the force is given back to me. That is why there is a negative sign. That is in the opposite direction. But what if I'm viewing it from the other side? Right, for the second body, it is positive compared to the first body. So there arises a confusion between whose perspectives are we talking about. Is it the first body's perspective? Is it the second body's perspective? I don't know. There is a confusion. There is a visible confusion. So there is one more thing we have to clearly justify. This confusion becomes more clearer when I ask you, okay, please tell me, is this particular object in rest or in motion? You can say, okay, when this is in my hand like this, is obviously in rest. But then my annoying little friend comes and says, okay, this is actually in motion because the earth is spinning and the earth is spinning around the sun, and the sun, the planets and every other things in the solar system is actually spinning itself and spiraling our galaxy, and the galaxy itself is spinning, and the entire Milky Way is spinning. Like everything is in motion. There is nothing in absolute rest. If you didn't know that, then please know that nothing is absolutely in rest. Then how can you say that, okay, this particular thing is in motion? Sorry, this particular thing is in rest. Or again, if you are sitting in a bus, for you, looking outside the window, everything is in motion. But for a person who's viewing you, then you are the person in motion. He is in rest. That is, to make it more clearer, imagine that I am traveling in a bus or a train. For me, I am sitting inside a bus or a train comfortably in my seat, which means that I am in a resting position. But if I view anything that is outside, I can see them moving apart. But for the person who is standing outside, just simply standing, he can say that, okay, I am actually in rest. That particular object or that particular person inside the bus is in motion. Am I wrong? No. Is the other person wrong? No. Both of them can be right? Yes. Both of them can be actually right. This is a concept that is known as relative motion. And in order to study relative motion or any other phenomena that include direction, forces and everything, we have to understand there is a particular frame we reference or particular frame we take in order to understand this particular observation. That particular frame is actually known as frame of reference, or simply we can say that it is the area under which we are doing the observation. For example, if I am saying that, okay, this is a bus, and I am sitting here. And I'm asking you, okay, this bus is not moving right now, it is completely at rest. And I'm asking you, okay, am I in rest? In order to answer that particular question, you need to have a frame of reference, which means that you're going to take a frame. In this particular case, it is the area surrounding this particular bus. It is the boundaries that contain this particular bus. Then you can clearly say that, okay, according to this frame of reference, I can say the bus is in rest. And if the frame of reference change at equal intervals of time, you can say, okay, it is relatively going in a motion, or it is having a relative motion. But again, if you don't have a frame of reference, the problem is that, again, my smart little friend will come and say, okay, you don't have a frame of reference, which means that you don't have a reference frame. You don't have anything to refer it with to, which means the earth is spinning, the galaxy is spinning, the solar system is spinning, so nothing is in absolute rest, so you cannot say that you are in rest. So to avoid all that confusions, we restrict our observational boundaries so that we can clearly define the motion of any object, or the parameters of any object can be clearly defined. For that, something we use is known as frame of reference, and this is known as a frame of reference. Frame of reference. There are actually two frame of references. One is generally known as inertial frame of references, and the other one is known as non-Newtonian frame of references. Or simply we can say that the frame of reference under which Newtonian laws are obeyed are known as Newtonian frame of references, or simply inertial frame of references. And the frame of reference in which Newton's laws are not obeyed is generally known as non-Newtonian frame of references. So anyways, that is all about frame of references. There is something known as frame of reference, and there are two frames of reference. One is inertial, where Newton's laws are completely obeyed, and there is another frame which is known as non-inertial frame of reference. Basically, in this frame, all of Newton's laws are obeyed, and in non-inertial frame of references, Newton's laws are not obeyed. We will be only focusing on the frame of reference in which Newton's laws are obeyed. And remember, frame of reference is there so that we can clearly define our equations and apply our equations. Otherwise, there will be problems. If an object is in continuous motion all the time, we cannot apply anything, any concepts of rest onto it. That is why we take frame of reference, so that we can apply the concept of rest and many other parameters onto that particular object. Anyways, we were talking about Newton's third law of motion and opposite directions, and we went to frame of references. So we say that Newton's third law of motion, the mathematical representation can be like this. If there is a force applied by the first body onto the second body, then we can say that the second body applies the same force onto the first body, but in the opposite direction. So that is Newton's third law of motion. And the sense of direction comes from, again, we learned in the first, second and third chapters that there is x, y and z axes. So this is y, this is negative y, this is negative x, and this is positive x. So again, if I am exerting a force in this particular direction, then the equal amount of force is being exerted in the opposite direction. That is why there is a negative sign. So remember, in physics, if a negative sign appears, It is just relatively indicating that the direction is opposite in nature. So if I'm applying a force in the positive x direction, the reaction force is in the negative x direction. That is why it is indicated through a negative sign, which means these are a pair of forces which are equal in magnitude. If you take the magnitude value of this particular forces, then both of them will be equal. Both of them will have equal forces, but the only thing is that it will be opposite in direction and the reaction force will be exerted by the second body onto the first body. That is the only difference. Otherwise, everything is equal. So simply Newton's third law of motion is, for every action, there is an equal and opposite reaction. Finally, we are going to discuss Newton's second law of motion, and this is the last Newton's law we are going to study here in this particular class. So we can say that Newton's second law of motion states that the rate of change of momentum of any object is actually directly proportional to the external force that is applied onto the object. That is, mathematically, I can say that force is directly proportional to rate of change of momentum. D by dt just means that it is the time derivative, or simply we can say rate of change. If any quantity is divided by time, you can say that it is a rate of change. Here, this particular quantity, that is, here P is indicating momentum. So what momentum actually is will be discussed shortly, don't worry. But again, rate of change of momentum is directly proportional to external force that is applied. So, okay, I'll do one thing. I'll explain momentum. What exactly is momentum? So, what exactly is momentum? Momentum indicated by the letter P is actually a vector quantity, which means it has a particular value, it has a particular direction, and it obeys laws of vector addition. So, can be indicated as mass times velocity. That is, to simply say, if there is any mass, let's say this is an object, let's say it's a ball, and this particular object which is having a mass m is there, then we can say that it gains momentum when it is in motion. Momentum is a fundamental property of any object that is having a mass and that is in motion, that is having a velocity. So if this particular ball moves in any particular direction, I can say that this particular object which is having a mass of m is moving with a standard velocity of v. Then I can say that the momentum of this particular quantity is given by mv. So just remember, momentum is a fundamental quantity which quantifies or which explains nature of motion of any object that is having mass. So we can actually say that if any object is moving, it has momentum. So any object with mass m is moving with a velocity v. It possesses a certain quantity or certain privileges that is indicated by the letter P, and that is known as momentum. If any object is moving, it has momentum. So it will be a product of the mass and velocity. For example, if any object which is having a low mass is traveling with a high velocity, again it will have high momentum. If any object is having large mass and moving slowly, also it will have high momentum. For example, if a bullet is coming at you at, let's say, 1 kilometer per second, it will have a lot of damaging power because it has a lot of momentum. Bullet is comparatively very small, but since it is coming at you with a huge amount of velocity, a huge amount of speed, that is why it is piercing through anything that you are wearing and giving you that particular energy, that is imparting that momentum onto you, giving you a lot of damage. But let's say, okay, if I reduce the velocity, will the momentum decrease? Not exactly, because if an elephant is coming at you, let's say at 5 meters per second, will you say that, okay, it is coming very slowly, it won't do anything to me? No, because the mass of the elephant is actually really high. That is why. So again, if the moon is falling onto you, let's say very slowly at 5 meters per second, will you say the same thing? Because it's coming very slow, it won't do anything to me? No, because it is coming at you with a high mass which you cannot actually support. Just like that. If velocity increases, momentum can increase. If mass increases also, momentum can increase. If simultaneously they both increase, momentum will be very large. If simultaneously they decrease, momentum will be very less. If mass decreases and velocity increases proportionally, that is, if mass decreases and velocity increases proportionally, momentum will be the same. That is, a small bullet having high velocity will have same damage as a high mass elephant, or elephant having higher mass moving with a slow velocity. Momentum is just a term indicating how fastly an object is actually moving and how much energy it can impart. All that can be related through momentum. So momentum is a quantity that defines motion, actually, that defines energy and motion, and all these principles can be explained using momentum. So now you understood what is momentum. What is Newton's second law stating? It is stating that force, especially external force, is directly proportional to rate of change of momentum. So what is this rate of change of momentum? Is directly proportional to force. That means that, okay, let's take an ideal condition. Let's take an ideal condition where an object, let's say this is an object having mass m. It is uniformly moving forward or in this particular direction with velocity v. So we can say that it is in uniform motion. So we know from Newton's first law of motion that unless I apply a force onto it, this particular object will move with that particular velocity throughout its life. So what Newton's second law is actually stating is that if I apply a force, I can actually change this particular body's momentum. That is, imagine that an object is moving like this. If no external force is applied by Newton's first law, it is going to move in that particular path. But if I apply a particular force onto this particular object, if I'm trying to catch it, if I'm trying to push it, if I'm trying to deviate it from its particular trajectory, I have to apply a force. So when I'm applying that particular force, what happens? Its momentum actually changes. That is because when the object is coming with a particular velocity, I'm applying an external force. Then I can actually vary or influence its velocity. So if I can influence its velocity, thereby I'm changing its momentum, because momentum is m times v. Even though I cannot change the mass, I am changing the velocity. So since I'm changing the velocity, the net momentum, which is indicated by P, is again changing. That is why I can change the momentum of this entire quantity by just applying an external force. And what Newton observed and stated is that the rate of change of that particular momentum, that is, how much I can change the momentum of that particular particle with respect to time, is actually directly proportional to the force which is applied onto that particular object. If an object is coming like this, I apply a small force, then the momentum is only decreased by a small factor. If an object is coming and apply a lot of force, then the momentum is changing drastically. That all depends upon the external force I am applying. So you can clearly say that force is directly proportional to the change in momentum, the rate of change of momentum. That is, with respect to time, the change in momentum depends on the force I am applying. So mathematically, you can actually represent it as F is directly proportional to dP by dt. Again, you have a small derivation also in this particular part, which is very simple. You just write down, that is, P is equal to mv. So we know that F is directly proportional to dP by dt, or simply dmv by dt. And we know that a derivative sign or a derivative operator can only operate if there is a varying quantity within that. Here, mass is not the varying quantity, but velocity is the varying quantity, which means mass is a constant quantity. If there is any quantity that is a constant quantity inside this particular operator, it is going to come right outside. So we can write it as F directly proportional to m dV by dt. So what is m dV by dt? Rate of change of velocity. Rate of change of velocity is nothing but acceleration. So we can actually write it as F is equal to m into A. We can simply say that F is equal to ma. That is Newton's second law of motion. So again, simply we can say that Newton's second law of motion can be derived like this. That is F directly proportional to dp by dt. But we know that momentum is equal to mass times velocity, which means F is directly proportional to dmv divided by dt. Again, m is a constant, mass is not changing. Velocity is a varying quantity, velocity is changing, which means mass comes right outside and velocity stays right where it is. So we can actually write it as F directly proportional to m dv by dt. And we know that dv by dt is nothing but rate of change of velocity. Rate of change of velocity, that is equal to acceleration A. So dv by dt can also be said as acceleration. dv by dt is actually equal to acceleration. So we can say that directly proportional to ma. And again, there is a proportionality sign here. In order to avoid the proportionality sign, we can just simply introduce a proportionality constant, which is k. And here the value of k is actually equal to 1. So we can write F is equal to ma. So that is where the famous equation F is equal to ma came from. So we came from actually Newton's second law of motion. So we can actually say that Newton's second law of motion is F is equal to ma. The actual definition is rate of change of momentum is directly proportional to external force applied, and the derivation gives you Newton's second law of motion. That is all about Newton's first, second and third law. I hope you have understood about these equations and the concepts regarding Newton's laws or Newtonian laws of motion. That is all for today. I'll see you again in the next class with a lot of interesting concepts from Newtonian mechanics. So I hope you do realize that all these three equations actually paved way for the Industrial Revolution. So many things you actually yearn for right now. For example, the Industrial Revolution actually took place only because Newton's second law existed. So please understand the importance and study well. I'll see you all in the next class. Thank you.